let me see. The question we were just talking about is what references did you use? Let me show you the very first reference that I checked. Like the moment I understood your thing. Actually, let me back up. Let me make a statement for some of the people who have criticized you in the past. That the criticism that I hear is he's not thinking in 3D. I hear that. He's not thinking in 3D. And I'm going to say, as I laid this out, I thought to myself, yeah, that seems right. And it didn't immediately strike me that there was any 3D missing from your analysis. And so the next thing I said, well, let's just check it. Let's just check it. So I took the chart you sent me, which was for Kabul, Afghanistan. And let me share my screen here. Sharing that. And I just went to SunCalc. I said, hey, it's not like this is not known, right? The position of the sun is well known. SunCalc, Stellarium, most people, you got a phone, get a planetarium app. It'll tell you where the sun is, right? It'll tell you where the sun is anywhere on the planet at any moment. So I just punch in Kabul here. And so that's going to be like city center. It won't be exactly where you're at. So it could be, you could be way over here or way over here. You can punch in your exact latitude and longitude though, if you want. But like I said, a couple of degrees, I'll just spot you that. I'm just going to spot you a couple of degrees. It's fine. And then it'll tell you when local noon is. Oh, you have to choose the date. So June 19th, 2020. I got the wrong year. June 19th, 2020. Let's punch that in. Oh, come on, 2020. Hello. Now I broke my SunCalc. How did I do this? There we go. 2020, go. Take the time. It's not taking it, y'all. June 2020. Okay, there we go. And the 19th. There you go. Got it. And it'll tell you local noon here. What year on year. Guess what? It's about the same. It's fine. So we've got it set for local noon. Little diagram and everything. And it tells you the altitude of the sun. And I say, oh, but I want 3 hours later. Or really just 1500. You said it was 1500. That's 1502. 1500. Oh my God, there. Okay. And sure enough, the altitude says 48 degrees. Exactly what you measured. So, so now I come right back to it and I say, okay, Corey's measurement matches SunCalc. So this improves my faith in SunCalc. SunCalc and Corey, they're on the same page. But according to our logic, we said that it couldn't be greater than 45 degrees. But SunCalc says that it is. And SunCalc is based on the globe. And so your model, so this is the thing, did you do this? Did you just go and punch it in and say, hey, is this what the planetarium software, is this what SunCalc says?
So in other words, so now we get to, remember when I sent you that email, got to do the field work. In other words, calculators are nice, but what does the on-ground tell me? So now,
yes, but your on-ground matches the calculator.
No.
Yeah, exactly.
So look at your position of the sun. Where's it at? You're in the center of Kabul.
Yeah.
I'm about 20 miles east of that.
Like I said, I'll spot you a couple degrees. I'll spot you a couple degrees if you want them,
okay,
but you don't need them. You're right on.
What I'm going to show you is
no. Hold on. No, I don't want to get off point. You did not look at this calculator. Is that what you're saying, or are you saying you just dismissed it as wrong?
Why would I?
Why would I? Okay, fair enough. Why would you? Is because I would think you want to check your logic. This is what I'm doing. when I get your data,
Mm-hmm.
I'm checking your data against the prediction. This is the globe prediction. The globe prediction is 48.39 degrees. Your measurement was 48 and change. That's confirmation.
So now what you're telling me is SunCalc just disproved the globe.
Okay, rolling back to what we said, there were two possibilities. Your measurements were wrong, or your logic was wrong.
Yeah.
Or actually, well, we dismissed the measurements. This is why I dismissed that your measurement is not wrong. There was a third, right? Mm-hmm. Your logic was wrong, or the model is wrong.
Mm-hmm.
This prediction, my understanding, right? I haven't actually gone into the source code for this. Mm-hmm. My understanding is that this prediction is based on the globe, and every other prediction from, you can check them all, Stellarium or astronomers, right? Astronomers, backyard astronomers with solar telescopes. Are you aware that just regular consumers can buy a solar telescope, a computerized tripod, that will look at the sun?
So here's the problem with, and the heliocentrists get in trouble with this. In other words, they don't know how to do line of parallel, and it gets them in trouble. And this is a prime example. In other words, from the observer position at 3 hours, you are 45 degrees.
No, not according to the actual globe model. Here's the actual globe model.
So
you presented.
Here's what I'll tell you.
Hold on. What you presented was your interpretation of the globe model.
Well, no, the mathematics also works.
Actually, it doesn't.
Sure.
You made a mistake. Are you ready for this?
Go ahead.
Okay. I showed you this before.
Mm-hmm.
I made a model. I made the globe model. Let's let the viewers see the model real quick. Mm-hmm. It's not to scale where I put the sun, right? I wanted it small enough you could see. So here's the Earth. You can make the Earth go around the sun like so. Boom, 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 boom. I've programmed it so that these beams, zoom in on the Earth here a bit, these beams are pointed the way the globe model says the beams should be pointed, which is back towards the sun, parallel. They are lines of parallel. Mm-hmm. Okay? All right, and I have put, you may recognize, I don't know where, but everybody knows, this one is in Kabul. Mm-hmm. This one is at the subsolar point below Kabul, south of Kabul.
Where at?
I don't know, wherever that happens to be. Oh, by the way, I should say, where I have this model set right now is for the June solstice. So 2 days after you took your measurement. 3 days after you took your measurement.
So the one, where's the Tropic of Cancer?
Right there.
Mm-hmm.
This one happens to go right through the Tropic of Cancer.
Mm-hmm. Okay.
All right. And what I put a little ball there, and I put a plane, because what I want to show is how this all works, right? I wanted to show that this beam is perpendicular to the surface, and that this beam is not perpendicular to the surface. Can you see that okay?
Yeah. Turn that back around.
So.
Okay. Keep turning it.
Okay.
Okay. So you're at the start point. Okay. So your subpolar plot, you're at the start point. So now your subpolar plot needs to go 3 hours beyond that. So for your east or your westerly reading, you're going to be over in Africa. So that bottom yellow line is going to be over in Africa.
Okay, what I'm going to do with my sim is now I am going to pin these 2 points and then roll us forward 3 hours and see what happens. Fair enough?
Yeah, sure. Go ahead. I'm watching.
Okay. And if you're curious, these are the angles that I'm calculating. And I do want to stress that I am not calculating the angle and than putting the sun there. What I'm doing is pointing the rays back towards the sun, and then reversing out, measuring out essentially what angle that is. So I've labeled this as Kabul. At Kabul at noon should be at 79 degrees, and subsolar point is there. So to get that, let's see here. Let's dig down into, here's Earth rotation. So if I want to go, I forgot which way is positive. Yeah, I got to go negative to get it to go east. Okay, so I'm going to subtract 45 degrees. I just typed it in there, minus 45. We see that the Earth has rotated 45 degrees.
Can you put grids on there?
Grids.
Yeah.
Not instantly. No. Not instantly. I could add those later. I do have, let's see, I do have these if you want. I have latitudes for those two particular spots. Does that help? That help?
Yeah. No, because I'm looking at your longitudes.
Oops. Oh, come here. There you go. So there's the longitude lines for, that's the Tropic of Cancer there. That's the longitude of Kabul. Latitude of Kabul.
Your longitude or your other way?
Longitude, yeah, they're just straight north-south.
Yeah.
So, I have them punched in if you want to see, like if you're thinking maybe those are wrong.
No, I'm just for reference.
Okay, longitude, I put 69.21, which I think was Kabul. I just looked it up. I'm in the city center. I didn't know exactly where you were at.
Yeah.
So, okay, and look what I see. I see at the solstice, 49 degrees. According to globe theory, this is the globe model. This is the globe model right there. And the 45-degree thing that you said isn't correct.
You got a problem. And that's the problem with the heliocentrists. They don't understand the limit of their model.
Okay, let me go on and make a few more points before you criticize my understanding of my own model.
Go ahead, keep going.
I would like to ask the next question, which is, how long is a summer day?
Well, I look at a day as 24 hours.
How long is the sun above the horizon in the summertime?
Well, it depends. In the summertime, depending on what part of the summertime, beginning summer.
Yeah, that's correct. It depends on the day of the year. And it also depends on your latitude.
Well, again, observer position is everything.
That's right. That's right.
That's why you want your survey point.
Rob is asking, what is the software? This software is called Unity 3D. I like to use it. It's free. Pretty easy to learn. So, yeah. Okay. So back to the topic of summertime. You agree that summer is longer than winter, as far as, sun being above the horizon. In winter, the days are shorter.
Sure.
Right?
Sure. We can visually see that.
So your measurements were taken very close to the summer solstice. And we found that at the summer solstice, which is what this is modeling here, the days are longer than 12 hours, meaning that 6 hours after noon, the sun is still up. 6 hours after noon, according to our previous slide, we had worked out the sun's got to be below the horizon. But globe Earth math says, no, that's not correct. And let me show you. I'll show you right here. Let's just go to, instead of going, let's just go another 45, right? Let's just take another 45 degrees. I think you can see in this view, it's still, this one right? The subsolar point is almost about to go into twilight. Kabul is still in the daytime, which, as we know, is true, right? We know that summer nights go, the sun's up late, right?
You can get sunlight all the way up probably around 9 in the evening. You can still see light.
Right. And so let me just pin that for a moment. Let's just slam the brakes on this whole conversation. Up in the northern hemisphere, the sun's up until like 9 at night sometimes. That means the sun does not move across our horizon at 15 degrees per hour. Just does not. That's wrong.
Well, you'd have to show that in timing, because my timing shows that it does.
Well, I'm showing it.
You're using a computer program, but you're going to have to show me some field work to support that, and you haven't shown me.
But you did the field work for me. Let me ask you to back up. Let's back it up and remind you that we had agreed there were two possibilities, that either the model was wrong or your analysis of the model, your logic was wrong.
Well, I think your model's wrong.
Okay, I understand that. Let me show you first this chart. The angle that you measured is labeled angle. The angle that the model predicts, the actual globe model, predicts, is in the globe column. And then for error, I showed the difference between those. And so on the 19th of June, your measurement matches the actual globe prediction precisely. My logic goes like this. When I got your numbers, first step, I compared against the published numbers, and I found that the published numbers match Corey's numbers. Step one. So whatever you measured confirms that the published numbers are accurate. Can we agree to that?
Confirms what?
Your measurements confirm that suncalc.org reported accurate numbers.
Based on what?
They were the same as yours.
And they exceed the globe model.
We're not there yet. We have to
we most certainly are.
The logic, the method of logic, right? The method of logic is to start with one point and then build from that to the next point, so that the way you've constructed this connection, it is true. Okay? So we're going to start from something we agree is true and build a connection to the next most logical step. We agree that you measured 48.4 degrees, was it?
Yeah, there are some readings over 50 degrees.
On the particular day, I'm just choosing one day. On the 19th of June, you measured 48.4 degrees. Agreed?
Yeah, that's what you reported, yeah.
Okay. Suncalc.org says 48.4 degrees. Can we agree on that?
That's what your model, the globe model, says.
Well, that's what SunCalc says.
Okay, who's SunCalc?
SunCalc.org. That's what they say.
Okay.
It's also going to be, if you check any Stellarium or any other online calculator, it'll all tell you the same thing.
Gotcha.
Okay. So from that, I say that the logical connection now is they agree. The online calculator matches Corey's physical, real world, precise measurement. Can you agree to that?
Well, I'll tell you what I measured is on what I've gave you. So if your SunCalc says, well, that's what you should get, then I would question them saying, well, okay, if you're going to say it's 48, you've just blown your model out of the water.
Okay, but do you see how that's a leap forward in the logic that you're making? I'm trying to walk the logic baby step at a time, and then you're like, jump to the end. I don't want to jump to the end. I want to go one step at a time.
Look at your logic.
Let me illustrate the logic, the concept of logic again. I'm going to start from point A and then go to point B using a statement that if point A is true and that statement is true, then point B is also true. That's how logic works. Now, you seem to be going from point A straight off onto point E without doing the steps in between. Let's do something else. Let's look at this another way.
And thank you for showing me, because this is
let's be Santa Claus for a minute. Let's go up to the North Pole, everybody. We're going to go do it in the North Pole.
The globe model invalidates itself.
But it's interesting that you say that.
That's going to be my headline from.
I have a different theory.
I'm just funning with you, man.
No, I get it, and I love that we can have this conversation. No one's going to get angry, and we can tease. It's all good. It's all good, you guys.
Yeah.
I actually think, and this is what fascinates me. Uncle Drunkle, if he's still in here, he always teases me that I'm just way too into the flat Earth. The thing that fascinates me is that your model is wrong, and I can show that. Not only can I show that your model is wrong.
Well, if I knew
can
that,
show that you know that.
I wouldn't have came on your show and was saying, "Hey, Matt, I just wanted to come on your show and let you know that my model's wrong."
Let me take you through how I work that out.
Somebody will get a soundbite off of that and they'll go, "Yeah, you admitted it on Matt's show."
Yeah. Okay, I've got one up in the North Pole. Right? I got one up at the North Pole.
Oh man.
Okay.
You must like the North Pole.
I do, because it's the extreme. It's the most extreme moment. Something that I've learned over the years is that when you're stuck on like a geometric puzzle and you're like, how does this even work? If you push it to the limits, you start to see how your assumptions about the geometry break down. So let's push it to the limit. The farthest limit is the North Pole. So I've just thrown a dot up on the North Pole. And you see the beam of light pointing back to the sun. Is that beam of light above the horizon?
Say again now.
This beam of light right here, pointing back to the sun from the North Pole. So if you did your observation at the North Pole on the summer solstice, the sun at this time, like we're still at 45 degrees later. The sun has rotated, or the Earth has rotated 45 degrees. 3 hours. We're at 3 o'clock afternoon. The sun is above the horizon. You agree?
When you talk about that beam of light, now, are you going to give me a measurement? Are you going to say like, well, this is this height? Are you going to ask me that, or what are we talking about?
I'm just asking if the sun is above the horizon at the North Pole at 3 p.m.
No, I've seen video and camera footage, from people fishing in the fall and stuff. So I would say, yeah, that the sun is visible, at extreme hours. So
I would like you to sort of reset your brain. We're criticizing the model, not at the moment. Let's just set aside reality. There is no reality. We're not going to talk about reality. We're going to talk just about this model. Does this model say the sun is above the horizon? And do you understand why it would say such a thing?
Now, here's another thing. When you say above the horizon, what are we defining as horizon? 0 degrees?
Yes. This little green plane,
right,
represents a horizon there.
Okay. So now your beam of light's going to have to go 0 degrees because you're higher than 0 degrees.
I don't understand what you mean. The beam of light is above this green plane, right?
Yeah. So what angle is your beam of light at?
Let's find out. I have added a label NP here at the top that shows the angle of the sun above the North Pole, above the horizon at the North Pole. And it's 23.5 degrees, which is an interesting coinky-dink of a number. right? You know what 23 and a half degrees is?
So is that line 0 degrees, or is that line at 23 degrees?
Is that line at 0 degrees, or is it that line is pointing straight back towards the sun?
I know. What's the angle though? What's the angle from the North Pole? What degrees is it?
23 and a half degrees from the horizon. Above.
Okay, so now remember, your sun is at 90 degrees. Now you're telling me that you're looking at the sun at 23 degrees. So that's quite an elevation. That's not 0 degrees.
That's right. That's the prediction.
So put your sun at 0 degrees, because we've got to be at 0 degrees at the horizon. You're at 20.
No, this is the North Pole, right?
Yeah.
And your understanding of the globe model includes that the Earth is tilted towards the sun at 23 and a half degrees in the summer on the northern hemisphere, right?
Well, yeah, but you got to get the sun at 90 degrees. So you just leave your sun at 90 degrees.
23 and a half degrees. This is the pole. That's what this gray line is. It's the north-south pole.
So now from your position on ground, because you're standing, what you're telling me is you're standing on ground at the North Pole at a 23-degree cant.
What is it? What do you mean 23-degree cant?
In other words, your axis is tilted 23 degrees, okay? So now,
okay,
if I'm on that,
I'm standing.
If I'm physically standing on the ground and I shoot a line directly ahead of me, is that heading at 0 degrees?
Yes, that's 0 degrees.
So
this green thing is the plane of your local horizon.
Yeah. So you need to put that yellow line up by the North Pole at 0 degrees, not 23 degrees.
Here, how's that? And I want, there you go.
Yeah, that looks better.
There. The sun is up above the horizon. Does that help you?
Yeah. So now that observer is looking at 0 degrees out. Okay.
Okay. This is 0 degrees right here. And they see the sun is above the horizon.
That model on your right side is not 0 degrees. Well, unless it's.
This is 0. I don't know. It looks like maybe it's tilted a little bit.
Yeah.
Like that. I don't know.
Okay.
Okay. You see what we're talking about here?
All right. Now go back over what we were talking about. Just refresh, because we got.
Okay. I have a very simple point I'm trying to make, which is on the summer solstice, right? On the summer solstice, this model with the sun, or with the Earth tilted towards the sun, the North Pole is tilted towards the sun by 23 and a half degrees on the summer solstice. Do you agree with that? That's what this model says.
It's got to. Yeah.
Okay.
The globe model.
So that means throughout the day, no matter what I do to the Earth throughout the day, the sun stays 23 and a half degrees above the horizon all day long, according to this model, because it's tilted towards it. It's like it's spinning.
Right.
Okay.
Okay.
It never changes from 23 and a half. Even though down here, down in Africa, in Egypt, it looks like the angle changes throughout the day. Right? At some times of the day, Egypt has the sun at a higher angle than the North Pole. At other times of the day, Egypt has the sun at a lower place than the North Pole. As we've just seen, we made this assumption early on that anywhere that is not at the sun's latitude, the latitude where the sun is at 90 degrees, anywhere that's not that, we had made the assumption that the sun is always lower than it is at that latitude. But the problem is, we showed that at the North Pole latitude, straight up 90, that wasn't true. So this statement 4, I think there can be no argument. That statement is wrong.
What was
statement
statement
just
4? What
wrong.
was statement 4 again?
Statement 4 is anywhere that is not at, I'm calling it that latitude, the latitude where the sun is at 90 degrees. So on the solstice, that is the Tropic of Cancer. Anywhere that is not the Tropic of Cancer.
Well, you have to look at time.
The assumption we have made is that all day long, the sun is always lower than it is at the Tropic of Cancer. But that is not true. Okay, so we strike that. And as soon as we strike it, we have to strike number 7 and we have to strike number 8. We were wrong. This whole sector test is based on bad assumptions. I showed SunCalc, showed you what the actual prediction says. The actual prediction for 1500 on June 19th of 2020 matches to the 10th of a degree your measurement. The actual prediction does not say the sun cannot go below 45 degrees. That is not what the measurement, that is not what the model says. It was a misunderstanding of the model. And it turns out the math is not trivial, but I looked it up. I looked it up and I found this website, PV Education. So what is PV Education? They're selling solar cells, or they're talking about solar cells. Do you want to buy a solar panel for your roof? You want to know what is the angle to the sun. So they got it, right? They know the angle to the sun because, right? Solar panels. And they've got the math for you on there. And there it is.
The sun can be used for many good things.
Yes. That is the equation for the angle of altitude of the sun.
Looks pretty impressive to me.
Right. So, yeah, spherical trig, Rob Parsons, spherical trig, woohoo! Yeah, you plug in your, the declination here. Oops, I'm in the wrong thing. Your declination, can you see that? Yeah. Declination goes in there, and that's the time of the year, basically. Or it comes from the time of the year. This is your latitude.
That looks like a flat Earth model. You got the firmament. You got the
yeah, it looks like a flat Earth model. It really does. And if you go to that website, it's even it's got a little, it'll sweep it across for you and show you how it works. And then you plug in the HRA. That's the angle based on the time of day. So you take the 15 degrees per hour, and that goes in there into HRA. So you plug that in, and that's the actual, that right there is the actual globe model. So I would encourage you to go to that website, look at that formula, get a calculator, plug it in to your Kabul observations, and show that that it is above 45 degrees in the summer because of the axial tilt. You need to, before you even go there, you need to check, is this actually correct in multiple ways?
From what?
So the first thing I checked was sunCalc.org, and it shows you're not correct. The second thing I did was derive the formula, and the formula I derived matches SunCalc and shows you're not correct. The third thing I did was look up online what the formula is. It matches my derivation, it matches SunCalc, and it shows you're not correct. The fourth thing that I did was build a three-dimensional geometric model and check it. It shows you're not correct. It matches all the other things. Basic critical thinking. The reality doesn't match your expectation.